Alright, now we are on question 4. Thinking about using orange, well, yellow, golden yellow. So now I'm going to write back the equations at the top again. EH equal to MCAT. And you're going to get fed up, but this is a way of helping you to remember the equations. I want you to remember the equations so much. So EH equals to power times time. EH also equals to MV squared over 2, and EH is equal to MGH. Just remember that these two, this one deals with kinetic energy, this one deals with potential energy, and this one deals with power or work done. So this one is a A and a B question as well. So 4. How much heat is needed to change 5 grams of ice at 0 degrees Celsius to water at 50 degrees Celsius? This sounds like fun. So we have a temperature change. We're going from 0 to 50. So let's start with ice. So we have the ice. We always start with our diagrams because then we could see what's going on. So we have 5 grams. And the degree is 0 degrees. Remember, to come out of ice into water at 50 degrees, you have to pass through the phase change where there is no change in temperature. And so it will be icy water at this point. And then to reach to the 50 degrees, you surpass the 0 degrees water to get there. Okay, and this is 5 grams as well. So we're acting as if it's a closed system. So how much heat? So we have 2 arrows to tend to. So because there's no temperature change here, we're not going to use MCAT. So we're going to use, because it's solid to liquid, we're going to use MLF. Remember, it's latent heat of fusion. So we put that here. And this is solid to liquid and liquid to solid. And this is gas to liquid, and this is liquid to gas. Mind you, we're going to have to use this eventually, so it's not just there for style. So we're going to work on this one is MCAT, because this is a change in temperature. So A is now equal to, because I want to save space, I'm not going to write the equation. I'm just going to write down the numbers. So this is a mass times the latent heat of fusion of solid ice to liquid icy water. That's the joules per gram. And then for B, we're going to write 5 grams times the temperature. Well, let's think about the water first. So specific heat capacity of the water is 4.2 joules per gram degree Celsius, and the temperature change would be the warmer temperature subtracting the cooler temperature. Okay, and if we work that out now, we have 5 times 340. We get 1700 right there, and then we have 5 times 4.2 times 50. So it's all a process, and you get 1050 joules, and you just add both of them up to get the total heat needed. So A and B will be equal to the total EH, which would be 1700 joules plus 1050 joules. So 1700 plus 1050 is 2750 joules. Alright, so that's A. B, it says if a refrigerator cools 200 grams of water from 20 degrees Celsius to its freezing point in 10 minutes, how much heat is removed per minute from the water? So, oh no, they're going to include time now. The only equation that has time here is this one, equation number 4. Okay, so we're going to be looking at this equation now. But first, let's do our little map. So we're starting off with 20 grams of water at 200 grams of water at 20 degrees Celsius, and it's supposed to get to its freezing point. So we know that freezing point of water is 0. Okay, so before it gets to become ice, right, it has to pass through the freezing water, which is 0 degrees, 200 grams, and then now we need the ice to form. So it must freeze to form ice, right? And we have 0 degrees Celsius. So we have A and B, 2 arrows to look at. So if we're going from this point to this point, we know there's a temperature change because we're going from 20 degrees to 0 degrees. So we're going to use MCAT. And if we're going from this point to this point, there is no temperature change, there's just a phase change from liquid to solid. So therefore we're going to use MLF because it's liquid to solid. Okay, so for A, I'm not going to use the equation, you're just going to have to imagine it looking at this. So we're going to say mass, which is 200 grams, times 4.2 because we're dealing with water. The specific heat capacity, C, represents specific heat capacity, joules per gram degree Celsius, times the temperature change, which is 20 minus 0, and then B would be 200 grams times the latent heat of fusion of ice, which would be 340 joules per gram. And so we just work these out, and we're going to say A plus B will give us the total EH given off in 10 minutes. Okay, so if we work out these separately, we get 200 times 4.2 times 20 to give us 16,800 joules, and then we have 200 times 340 to give us 68,000 joules. Okay, and if you add these up now, you would get 68,000 plus 16,800, 84,800 joules, and that's in 10 minutes. So you could equate them. If you want to figure out per minute, you would say if this amount, if 84,800 joules is given off in 10 minutes, then X joules will be given off in 1 minute. And it's a simple division, right? So you would divide this by 10 and you get, this is what's going on. So basically this is going to cross multiply up here, this is going to come down, and the X is going to go up. So you're going to end up with this 84,800 joules times 1 minute over 10 minutes. The minutes cancel, so you're left back with joules, and you end up with 8480 joules. So per minute, that's how much heat is being given off to make ice. That's a lot, right? Okay, so moving on to question 5. I think I'm going to use a nice dark color now, purple. And I'm going to write back the equations at the top here. EH equal to MCAT. EH equals to MLF. EH equals to MLV. EH equals to PT. EH equals to MV squared over 2. And EH equals to MGH. So it says now, how long will it take a 50-watt heater to melt 100 grams of ice at 0 degrees Celsius? So there is no temperature change here. So basically we're going from ice. I like to draw. It's calming. So you're going from ice, 100 grams of ice at 0 degrees Celsius, to basically water, 100 grams of it at 0 degrees Celsius. So there's no change in temperature. So therefore you're not going to be using MCAT. You're going to be using MLF, because you're going from solid to a liquid. So let's not forget solid to liquid, and liquid to solid refers to this, MLF, LF. And this one, which is LV, refers to gas to liquid, or from liquid to gas. Okay? And so in this case, we're going to list all the stuff that we have. We have power. Power has units of watts. So we have power, which is 50 watts. And that is also equivalent to 50 joules per second, because 1 watt is actually equal to 1 joule per second. And then we have the mass. We have a mass of 100 grams. We're looking for time, because it says how long. How long asks us about time. So we're looking for time. If you look up here, you will see that this is the equation that we will dealing with. Now note well that EH can mean, you can substitute EH for MCAT, EH for MLV, or EH for MLF, right? But in this case, since we're dealing with MLF, EH equals to PT, and since we're looking for time and we read from left to right, I'm going to switch it around. PT equal to EH. And since EH is also equal to MLF, we could substitute and put it right in there. And we say MLF. And since we're solving for T, we leave T in the numerator and we divide both sides by P. So therefore T is equal to MLF over P. So if we fill it in now, we say the mass is 100 grams. The latent heat of fusion is 340, so I didn't put that in there. So I'm going to put that there to make it complete and nice and just. So we're going to say 340 joules per gram. And in the power, we're going to use joules and seconds, because we want to get rid of joules and we need the seconds to make sure our calculation makes sense to us. Now, what I often do with my students, I will tell them, take out the units and calculate the units. Like, get rid of whatever needs to be gotten rid of, so that you know what units are going to be left back. And so we say G over 1, because anything whole is over 1 anyway, times J over G. And since this is J over S, in the denominator is going to flip. And you're going to get S over J. Right? It's going to flip. And so if you look at it closely, you realize that everything goes except seconds. So your answer would be in seconds, which means that you're doing something right. And you calculate it now, you would get 100 times 340 divided by 50. So you get 600. You get 680 seconds. So that's how much time it would take to melt 100 grams of ice. Okay? This was a pretty nice one. So we're at number 6 now. By the way, there are 12 questions. I hope you are able to stick around with me. So it says some small aluminum rivets of total mass 170 grams and at 100 degrees Celsius are emptied into a hole in a large block of ice at 0 degrees. So we're going to take into account they're saying large block of ice. Okay? Because A asks, what will be the final temperature of the rivets? Now I'm going to make an assumption that block of ice is really big. It's huge. And so in this block of ice you have like maybe a deep groove. Okay, and probably the groove was drilled there. So you have this block of ice, and the block of ice is at 0 degrees Celsius, right? They put these aluminum rivets in here. And it doesn't matter how much I put, it's about the density of the rivets, right? So the mass of the rivets combined is actually 170 grams. Okay? Because of the large mass that the ice has, it's not going to be affected. It's not going to melt all the way down. It's going to actually, all the heat from the rivets is going to enter into the block of ice, causing the ice to melt somewhat, right? But it's still going to stay at 0 degrees Celsius. It's not going to affect the change in temperature. It's just going to change the solid ice into liquid ice, right? So we're going to have some melting happening in here. So this is just going to change the phase of the ice to water, and we can still have 0 degrees Celsius. Okay? So because it says a block of ice at 0 degrees, it doesn't have any temperature change for the ice whatsoever. However, we know that there will be some temperature change for the rivets. Okay? So the rivets went in at 100 degrees Celsius. Okay? So what will be the final temperature of the rivets? It will be 0, because eventually, remember, heat always leaves from hotter bodies to cooler ones, and then eventually what happens over time is thermal equilibrium, and in this case it's going to come to a thermal equilibrium of 0. So I'm going to say 0 degrees right here. How much ice will melt? So let's see how much ice will melt. We're first going to have to work out the amount of heat that's lost by the aluminum rivets. And if we do this, we see that we already listed all the things that aluminum has. So we know we have a mass of 170 grams. And remember, the aluminum is solid being hot and solid when it's cold. So there is no change in phase. So we're going to use MCAT. So mass times the specific heat capacity, which is 0.90 joules per gram degree Celsius. So that's C. And the temperature change would be 100 minus 0 degrees Celsius. And that's the delta T right there. And that would give us 170 times 0.9 times 100, and we have 15,300 joules. Now when you look at the ice, there was no change in temperature but there was a change in phase. Because remember, you had thermal equilibrium happening at the end. So with ice, you went from a block of ice to you went from a block of ice at 0 degrees Celsius to icy water at 0 degrees Celsius, right? And how much ice did we have? Well, we want to find out the mass, right? So since we didn't have a temperature change, we're gonna say we have MLF. Okay, and we could equate these to the heat lost by the aluminum will be the heat gained by the ice. And since we already worked out aluminum, we say 15,000 joules of heat was lost by the aluminum and gained by the ice. And we want to know how much ice melted. So if we M times the latent heat of fusion, because we went from ice to icy water at the same temperature. So we're going to use 340 joules per gram. And look at that, I didn't even put my equation at the top. I'm going to put them there in a while. And to solve for mass now, you divide both sides by 340 because you want to get mass. And remember, I told you if you take these units out, we have J over 1, that's this up here, times this, which you're going to split and cancel, so you're going to be left with grams. So the grams would be 340, you get 45 grams. So in good practice and keeping with the mole, I'm going to say, don't forget your equations of EH and cat. EH equal MLF, EH equal MLV, EH equals to PT, EH equals to MV squared over 2, and then EH equals to MGH. Don't forget this is from gas to liquid and from liquid to gas, LV, and this is LF, solid to liquid and liquid to solid. Okay, so you need to remember that.